Introduction to Quantum Mechanics. The goal of this text is to help readers understand the operation and characteristics of semiconductor devices. Ideally, we would like to begin discussing these devices immediately. However, in order to understand the current voltage characteristics, we need some knowledge of electron behavior in a semiconductor when the electron is subjected to various potential functions. The motion of large objects, such as planets and satellites, can be predicted to a high degree of accuracy using classical theoretical physics based on Newton's laws of motion. But certain experimental results, involving electrons and light waves, appear to be inconsistent with classical physics. However, these experimental results can be predicted using the principles of quantum mechanics. The behavior and characteristics of electrons in a semiconductor can be described by the formulation of quantum mechanics called wave mechanics. The essential elements of this wave mechanics, using Schrödinger's wave equation, are presented in this chapter. The goal of this chapter is to provide a brief introduction to quantum mechanics, so that readers gain an understanding of and become comfortable with the analysis techniques. This introductory material forms the basis of semiconductor physics. In this chapter, we will discuss a few basic principles of quantum mechanics that apply to semiconductor device physics, state Schrödinger's wave equation and discuss the physical meaning of the wave function. Consider the application of Schrödinger's wave equation to various potential functions to determine some of the fundamental properties of electron behavior in a crystal. Apply Schrödinger's wave equation to the one-electron atom. The result of this analysis yields the four basic quantum numbers, the concept of discrete energy bands, and the initial buildup of the periodic table. 2.1 Principles of Quantum Mechanics. Before we delve into the mathematics of quantum mechanics, there are three principles we need to consider: the principle of energy quanta, the wave-particle duality principle, and the uncertainty principle. 2.1.1 Energy quanta. One experiment that demonstrates an inconsistency between experimental results and the classical theory of light is called the photoelectric effect. If monochromatic light is incident on a clean surface of a material, then under certain conditions, electrons, photoelectrons, are emitted from the surface. According to classical physics, if the intensity of the light is large enough, the work function of the material will be overcome and an electron will be emitted from the surface independent of the incident frequency. This result is not observed. The observed effect is that at a constant incident intensity, the maximum kinetic energy of the photoelectron varies linearly with frequency with a limiting frequency 0, below which no photoelectron is produced. This result is shown in figure 2.1. If the incident intensity varies at a constant frequency, the rate of photoelectron emission changes, but the maximum kinetic energy remains the same. Planck postulated in 1900 that thermal radiation is emitted from a heated surface in discrete packets of energy called quanta. The energy of these quanta is given by, where is the frequency of the radiation, and h is a constant now known as Planck's constant. Then in 1905, Einstein interpreted the photoelectric results by suggesting that the energy in a light wave is also contained in discrete packets or bundles. Figure 2.1, a. The photoelectric effect, and b. The maximum kinetic energy of the photoelectron as a function of incident frequency. The particle-like packet of energy is called a photon, whose energy is also given by Eh. A photon with sufficient energy, then, can knock an electron from the surface of the material. The minimum energy required to remove an electron is called the work function of the material, and any excess photon energy goes into the kinetic energy of the photoelectron. This result was confirmed experimentally as demonstrated in figure 2.1. The photoelectric effect shows the discrete nature of the photon and demonstrates the particle-like behavior of the photon. The maximum kinetic energy of the photoelectron can be written as where hv is the incident photon energy and the minimum energy, or work function, required to remove an electron from the surface. Objective: calculate the photon energy corresponding to a particular wavelength. Consider an X-ray with a wavelength of 7.08 nanocentimeters 70.8 picometers. Solution. The energy is. This value of energy may be given in the more common unit of electron volt, see Appendix D. We have. The reciprocal relation between photon energy and wavelength is demonstrated. A large energy corresponds to a short wavelength. Wave-particle duality. We have seen in the last section that light waves, in the photoelectric effect, behave as if they are particles. The particle-like behavior of electromagnetic waves was also instrumental in the explanation of the Compton effect. In this experiment, an X-ray beam was incident on a solid. A portion of the X-ray beam was deflected and the frequency of the deflected wave had shifted compared with the incident wave. The observed change in frequency and the deflected angle corresponded exactly to the expected results of a billiard ball collision between an X-ray quanta, or photon, and an electron in which both energy and momentum are conserved. In 1924, de Broglie postulated the existence of matter waves. He suggested that since waves exhibit particle-like behavior, particles should be expected to show wave-like properties. The hypothesis of de Broglie was the existence of a wave-particle duality principle. The momentum of a photon is given by where is the wavelength of the light wave. Then, de Broglie hypothesized that the wavelength of a particle can be expressed as where p is the momentum of the particle and is known as the de Broglie wavelength of the matter wave. The wave nature of electrons has been tested in several ways. In one experiment by Davison and Germer in 1927, electrons from a heated filament were accelerated at normal incidence onto a single crystal of nickel. A detector measured the scattered electrons as a function of angle. Figure 2.2 shows the experimental setup and Figure 2.3 shows the results. The existence of a peak in the density of scattered electrons can be explained as a constructive interference of waves scattered by the periodic atoms in the planes of the nickel crystal. The angular distribution is very similar to an interference pattern produced by light diffracted from a grating. In order to gain some appreciation of the frequencies and wavelengths involved in the wave-particle duality principle, Figure 2.4 shows the electromagnetic frequency spectrum. We see that a wavelength of 72.7 A obtained in the next example is in the ultraviolet range. Typically, we will be considering wavelengths in the ultraviolet and visible range. Figure 2.2 Experimental arrangement of the Davison-Germer experiment. Figure 2.3 Scattered electron flux as a function of scattering angle for the Davison-Germer experiment. Figure 2.4 The electromagnetic frequency spectrum. These wavelengths are very short compared to the usual radio spectrum range. Objective: calculate the de Broglie wavelength of a particle. Consider an electron traveling at a velocity of 10 million centimeters per second equals 100,000 meters per second. Solution: the momentum is given by. Then, the de Broglie wavelength is. This calculation shows the order of magnitude of the de Broglie wavelength for a typical electron. In some cases, electromagnetic waves behave as if they are particles, photons, and sometimes particles behave as if they are waves. This wave-particle duality principle of quantum mechanics applies primarily to small particles such as electrons, but it has also been shown to apply to protons and neutrons. For very large particles, we can show that the relevant equations reduce to those of classical mechanics. The wave-particle duality principle is the basis on which we will use wave theory to describe the motion and behavior of electrons in a crystal. The uncertainty principle. The Heisenberg uncertainty principle, given in 1927, also applies primarily to very small particles and states that we cannot describe with absolute accuracy the behavior of these subatomic particles. The uncertainty principle describes a fundamental relationship between conjugate variables, including position and momentum and also energy and time. The first statement of the uncertainty principle is that it is impossible to simultaneously describe with absolute accuracy the position and momentum of a particle. If the uncertainty in the momentum is p and the uncertainty in the position is x, then the uncertainty principle is stated as where is defined as is called a modified Planck's constant. This statement may be generalized to include angular position and angular momentum. The second statement of the uncertainty principle is that it is impossible to simultaneously describe with absolute accuracy the energy of a particle and the instant of time the particle has this energy. Again, if the uncertainty in the energy is given by E and the uncertainty in the time is given by T, then the uncertainty principle is stated as. One way to visualize the uncertainty principle is to consider the simultaneous measurement of position and momentum, and the simultaneous measurement of energy and time. The uncertainty principle implies that these simultaneous measurements are in error to a certain extent. However, the modified Planck's constant is very small. The uncertainty principle is only significant for subatomic particles. We must keep in mind nevertheless that the uncertainty principle is a fundamental statement and does not deal only with measurements. One consequence of the uncertainty principle is that we cannot, for example, determine the exact position of an electron. We will, instead, determine the probability of finding an electron at a particular position. In later chapters, we will develop a probability density function that will allow us to determine the probability that an electron has a particular energy. So in describing electron behavior, we will be dealing with probability functions. Schrödinger's wave equation. The various experimental results involving electromagnetic waves and particles, which could not be explained by classical laws of physics, showed that a revised formulation of mechanics was required. Schrödinger, in 1926, provided a formulation called wave mechanics, which incorporated the principles of quanta introduced by Planck, and the wave-particle duality principle introduced by de Broglie. On the basis of wave-particle duality principle, we will describe the motion of electrons in a crystal by wave theory. This wave theory is described by Schrödinger's wave equation. The wave equation. The one-dimensional, non-relativistic Schrödinger's wave equation is given by where x, t, is the wave function, v, x, is the potential function assumed to be independent of time, m is the mass of the particle, and j is the imaginary constant. There are theoretical arguments that justify the form of Schrödinger's wave equation, but the equation is a basic postulate of quantum mechanics. The wave function, x, t, will be used to describe the behavior of the system and, mathematically, x, t, can be a complex quantity. We may determine the time-dependent portion of the wave function and the position-dependent, or time-independent, portion of the wave function by using the technique of separation of variables. Assume that the wave function can be written in the form where x is a function of the position x only and t is a function of time t only. Substituting this form of the solution into Schrödinger's wave equation, we obtain. If we divide by the total wave function, equation 2.8 becomes. Since the left side of equation 2.9 is a function of position x only and the right side of the equation is a function of time t only, each side of this equation must be equal to a constant. We will denote this separation of variables constant by the time-dependent portion of equation 2.9 is then written as where again the parameter is called a separation constant. The solution of equation 2.10 can be written in the form. The form of this solution is the classical exponential form of a sinusoidal wave. We have that at the separation constant is equal to the total energy E of the particle. We can then write. We see that n is the radian or angular frequency of the sinusoidal wave. The time-independent portion of Schrödinger's wave equation can now be written from equation 2.9 as where the separation constant is the total energy E of the particle. Equation 2.12 may be written as where again m is the mass of the particle, v, x, is the potential experienced by the particle, and E is the total energy of the particle. This time-independent Schrödinger's wave equation can also be justified on the basis of the classical wave equation as shown in Appendix E. The pseudo-derivation in the appendix is a simple approach but shows the plausibility of the time-independent Schrödinger's equation. Physical meaning of the wave function. We are ultimately trying to use the wave function, x, t, to describe the behavior of an electron in a crystal. The function, x, t, is a wave function, so it is reasonable to ask what the relation is between the function and the electron. The total wave function is the product of the position-dependent, or time-independent, function and the time-dependent function. From equation 2.7, we have: since the total wave function, x, t, is a complex function, it cannot by itself represent a real physical quantity. Max Born postulated in 1926 that the function is the probability of finding the particle between x and x dx at a given time, or that, x, t, 2 is a probability density function. We have that here asterisk, x, t, is the complex conjugate function. Therefore, then the product of the total wave function and its complex conjugate is given by is the probability density function and is independent of time. One major difference between classical and quantum mechanics is that in classical mechanics, the position of a particle or body can be determined precisely, whereas in quantum mechanics, the position of a particle is found in terms of a probability. We will determine the probability density function for several examples, and since this property is independent of time, we will, in general, only be concerned with the time-independent wave function. Boundary conditions. Since the function, x, 2 represents the probability density function, then for a single particle, we must have the probability of finding the particle somewhere is certain. Equation 2.18 allows us to normalize the wave function and is one boundary condition that is used to determine some wave function coefficients. The remaining boundary conditions imposed on the wave function and its derivative are postulates. However, we may state the boundary conditions and present arguments that justify why they must be imposed. The wave function and its first derivative must have the following properties if the total energy E and the potential V, x, are finite everywhere. Condition 1. X must be finite, single-valued, and continuous. Condition 2. X must be finite, single-valued, and continuous. Figure 2.5 potential functions and corresponding wave function solutions for the case, A, when the potential function is finite everywhere and, B, when the potential function is infinite in some regions. Since x, 2 is a probability density, then, x, must be finite and single-valued. If the probability density were to become infinite at some point in space, then the probability of finding the particle at this position would be certain and the uncertainty principle would be violated. If the total energy E and the potential V, x, are finite everywhere, then from equation 2.13, the second derivative must be finite, which implies that the first derivative must be continuous. The first derivative is related to the particle momentum, which must be finite and single-valued. Finally, a finite first derivative implies that the function itself must be continuous. In some of the specific examples that we will consider, the potential function will become infinite in particular regions of space. For these cases, the first derivative will not necessarily be continuous, but the remaining boundary conditions will still hold. Figure 2.5 shows two possible examples of potential functions and the corresponding wave solutions. In Figure 2.5a, the potential function is finite everywhere. The wave function as well as its first derivative is continuous. In Figure 2.5b, the potential function is infinite for x0 and for xa. The wave function is continuous at the boundaries, but the first derivative is discontinuous. We will actually determine the wave functions in the following sections and in end of chapter problems. 2.3 Applications of Schrödinger's wave equation. We will now apply Schrödinger's wave equation in several examples using various potential functions. These examples will demonstrate the techniques used in the solution of Schrödinger's differential equation, and the results of these examples will provide an indication of the electron behavior under these various potentials. We will utilize the resulting concepts later in the discussion of semiconductor properties. Electron in free space. As a first example of applying the Schrödinger's wave equation, consider the motion of an electron in free space. If there is no force acting on the particle, then the potential function V, x, will be constant, and we must have EV, x. Assume, for simplicity, that the potential function V, x, 0 for all x. Then, the time-independent wave equation can be written from equation 2.13, as the solution to this differential equation can be written in the form where and is called a wave number. Recall that the time-dependent portion of the solution is. Then the total solution for the wave function is given by. This wave function solution is a traveling wave, which means that a particle moving in free space is represented by a traveling wave. The first term, with the coefficient a, is a wave traveling in the x direction, while the second term, with the coefficient b, is a wave traveling in the x direction. The value of these coefficients will be determined from boundary conditions. We will again see the traveling wave solution for an electron in a crystal or semiconductor material. Assume, for a moment, that we have a particle traveling in the x direction, which will be described by the x traveling wave. The coefficient b equals 0. We can write the traveling wave solution in the form where k is the wave number given by, or combining equations 225a and 2.26, the wavelength can also be written in terms of the wave number as a free particle with a well-defined energy will also have a well-defined wavelength and momentum. The probability density function is x, t, a, which is a constant independent of position. A free particle with a well-defined momentum can be found anywhere with equal probability. This result is in agreement with the Heisenberg uncertainty principle, in which a precise momentum implies an undefined position. A localized free particle is defined by a wave packet, formed by a superposition of wave functions with different momentum or k values. We will not consider the wave packet here. The infinite potential well. The problem of a particle in the infinite potential well is a classic example of a bound particle. The potential V, x, as a function of position for this problem is shown in figure 2.6. The particle is assumed to exist in region 2, so the particle is contained within a finite region of space. The time-independent Schrödinger's wave equation is again given by equation 2.13, as where E is the total energy of the particle. If E is finite, the wave function must be 0, or x, 0, in both regions I and 3. A particle cannot penetrate these infinite potential barriers, so the probability of finding the particle in regions I and 3 is 0. The time-independent Schrödinger's wave equation in region 2, where V0, becomes figure 2.6 potential function of the infinite potential well. A particular form of solution to this equation is given by one boundary condition is that the wave function, x, must be continuous so that, applying the boundary condition at x0, we must have that a1 0. At xa, we have. This equation is valid if Kansas n, where the parameter n is a positive integer, or n1, 2, 3. The parameter n is referred to as a quantum number. We can write negative values of n, simply introduce a negative sign in the wave function and yield redundant solutions for the probability density function. We cannot physically distinguish any difference between n and n solutions. Because of this redundancy, negative values of n are not considered. The coefficient a2 can be found from the normalization boundary condition that was given by equation 2.18, as we assume that the wave function solution, x, is a real function, then x, x. Substituting the wave function into equation 2.18, we have evaluating this integral gives 3. Finally, the time-independent wave solution is given by here n1, 2, 3. 2.36. This solution represents the electron in the infinite potential well and is a standing wave solution. The free electron was represented by a traveling wave, and now the bound particle is represented by a standing wave. The parameter k in the wave solution was defined by equations 2.30 and 2.33. Equating these two expressions for k, we obtain the total energy can then be written as where n1, 2, 3. 2.38. For the particle in the infinite potential well, the wave function is now given by where the constant kn, from equation 2.37, must have discrete values, implying that the total energy of the particle can only have discrete values. This result means that the energy of the particle is quantized. That is, the energy of the particle can only have particular discrete values. The quantization of the particle energy is contrary to results from classical physics, which would allow the particle to have continuous energy values. The discrete energies lead to quantum states that will be considered in more detail in this and later chapters. The quantization of the energy of a bound particle is an important result. This quantization of electron energy will be observed again at the end of the chapter for an electron bound to an ion forming an atom. Objective: calculate the FeRST3 energy levels of an electron in an infinite potential well. Consider an electron in an infinite potential well of width 5 angstroms. Solution: from equation 2.38, we have this calculation shows the order of magnitude of the energy levels of a bound electron. Figure 2.7a shows the FeRST4 allowed energies for the particle in the infinite potential well, and figure 2.7b, c shows the corresponding wave functions and probability functions. We may note that as the energy increases, the probability of finding the particle at any given value of x becomes more uniform. The step potential function. Consider now a step potential function as shown in figure 2.8. In the previous section, we considered a particle being confined between two potential barriers. In this example, we will assume that a flux of particles is incident on the potential barrier. We will assume that the particles are traveling in the x direction and that they originated at a particularly interesting result is obtained for the case when the total energy of the particle is less than the barrier height, or EV0. We again need to consider the time-independent wave equation in each of the two regions. This general equation was given in equation. The wave equation in region I, in which is figure 2.7 particle in an infinite potential well, A, for lowest discrete energy levels, B, corresponding wave functions, and C, corresponding probability functions. The general solution to this equation can be written in the form where the constant k1 is. The first term in equation 2.41 is a traveling wave in the x direction that represents the incident wave, and the second term is a traveling wave in the x direction. Figure 2.8 the step potential function. That represents a reflected wave. As in the case of a free particle, the incident and reflected particles are represented by traveling waves. For the incident wave, A1 is the probability density function of the incident particles. If we multiply this probability density function by the incident velocity, then A1 is the flux of incident particles in units of number/centimeter 2s. Likewise, the quantity VrB1 is the flux of the reflected particles, where Vr is the velocity of the reflected wave. The parameters 6 and Vr in these terms are actually the magnitudes of the velocity only. In region 2, the potential is VV0. If we assume that EV0, then the differential equation describing the wave function in region 2 can be written as. The general solution may then be written in the form where one boundary condition is that the wave function 2, x, must remain finite. Which means that the coefficient b2 0. The wave function is now given by. The wave function at x0 must be continuous so that. Then from equations 2.41, 2.46, and 2.47, we obtain. Since the potential function is everywhere finite, the first derivative of the wave function must also be continuous so that. Using equations 2.41, 2.46, and 2.49, we obtain. We can solve equations 2.48 and 2.50 to determine the coefficients b1 and a2. In terms of the incident wave coefficient a1, the results are and the reflected probability density function is given by. We can define a reflection coefficient, R, as the ratio of the reflected flux to the incident flux, which is written as where I and R are the incident and reflected velocities, respectively, of the particles. In region I, V0 so that Et, where T is the kinetic energy of the particle. The kinetic energy is given by. So that the constant K1, from equation 2.42, may be written as. The incident velocity can then be written as. Since the reflected particle also exists in region I, the reflected velocity, magnitude, is given by. The incident and reflected velocities, magnitudes, are equal. The reflection coefficient is then. Substituting the expression from equation 2.52 into equation 2.58, we obtain. The result of R1 implies that all of the particles incident on the potential barrier for V0 are eventually reflected. Particles are not absorbed or transmitted through the potential barrier. This result is entirely consistent with classical physics, and one might ask why we should consider this problem in terms of quantum mechanics. The interesting result is in terms of what happens in region 2. The wave solution in region 2 was given by equation 2.46 as A2 EK2x. The coefficient A2 from equation 2.48 is A2 1B1, which we derived from the boundary conditions. For the case of EV0, the coefficient A2 is not 0. If A2 is not 0, then the probability density function 2, x, 2 asterisk, x, of the particle being found in region 2 is not equal to 0. This result implies that there is a finite probability that the incident particle will penetrate the potential barrier and exist in region 2. The probability of a particle penetrating the potential barrier is another difference between classical and quantum mechanics. The quantum mechanical penetration is classically not allowed. Although there is a finite probability that the particle may penetrate the barrier, since the reflection coefficient in region I is unity, the particle in region 2 must eventually turn around and move back into region I. Objective: calculate the penetration depth of a particle impinging on a potential barrier. Consider an incident electron that is traveling at a velocity of 105 m/s in region I. With V, x, 0, the total energy is also equal to the kinetic energy so that. Now, assume that the potential barrier at x0 is twice as large as the total energy of the incident particle, or that V0 2e. The wave function solution in region 2 is where the constant k2 is given by k2. In this example, we want to determine the distance xd at which the wave function magnitude has decayed to e1 of its value at x0. Then, for this case, we have k2d1 or. This penetration distance corresponds to approximately 2 lattice constants of silicon. The numbers used in this example are rather arbitrary. We used a distance at which the wave function decayed to e1 of its initial value. We could have arbitrarily used e2, for example, but the results give an indication of the magnitude of penetration depth. The case when the total energy of a particle, which is incident on the potential barrier, is greater than the barrier height, or EV0, is left as an exercise at the end of the chapter. Figure 2.9 The potential barrier function. The potential barrier and tunneling. We now want to consider the potential barrier function, which is shown in figure 2.9. The more interesting problem, again, is in the case when the total energy of an incident particle is eV0. Again, assume that we have a flux of incident particles originating on the negative x-axis traveling in the x direction. As before, we need to solve Schrödinger's time-independent wave equation in each of the three regions. The solutions of the wave equation in regions I, II, and III are given, respectively, as where and the coefficient B3 in equation 260c represents a negative traveling wave in region 3. However, once a particle gets into region 3, there are no potential changes to cause a reflection, therefore, the coefficient B3 must be 0. We must keep both exponential terms in equation 260b, since the potential barrier width is finite, that is, neither term will become unbounded. We have four boundary relations for the boundaries at x0 and xa corresponding to the wave function and its first derivative being continuous. We can solve for the four coefficients b1, a2, b2, and a3 in terms of a1. The wave solutions in the three regions are shown in figure 2.10. Figure 2.10 The wave functions through the potential barrier. One particular parameter of interest is the transmission coefficient, in this case defined as the ratio of the transmitted flux in region 3 to the incident flux in region I. Then the transmission coefficient T is where Vt and 6 are the velocities of the transmitted and incident particles, respectively. Since the potential V0 in both regions I and III, the incident and transmitted velocities are equal. The transmission coefficient may be determined by solving the boundary condition equations. For the special case when EV0, we find that equation 2.63 implies that there is a finite probability that a particle impinging a potential barrier will penetrate the barrier and will appear in region 3. This phenomenon is called tunneling and it, too, contradicts classical mechanics. We will see later how this quantum mechanical tunneling phenomenon can be applied to semiconductor device characteristics, such as in the tunnel diode. Objective: calculate the probability of an electron tunneling through a potential barrier. Consider an electron with an energy of 2 electron volts impinging on a potential barrier with electron volts and a width of 3 angstroms. Solution: equation 2.63 is the tunneling probability. The factor K2 is then. And finally, the tunneling probability may appear to be a small value, but the value is not 0. If a large number of particles impinge on a potential barrier, a significant number can penetrate the barrier. Additional applications of Schrödinger's wave equation with various one-dimensional potential functions are found in problems at the end of the chapter. Several of these potential functions represent quantum well structures that are found in modern semiconductor devices. Extensions of the wave theory to ATOMS5. So far in this chapter, we have considered several one-dimensional potential energy functions and solved Schrödinger's time-independent wave equation to obtain the probability function of finding a particle at various positions. Consider now the one-electron, or hydrogen, atom potential function. We will only briefly consider the mathematical details and wave function solutions, but the results are interesting and important. The one-electron atom, the nucleus, is a heavy, positively charged proton and the electron is a light, negatively charged particle that, in the classical Bohr theory, is revolving around the nucleus. The potential function is due to the Coulomb attraction between the proton and electron and is given by where E is the magnitude of the electronic charge and 0 is the permittivity of free space. This potential function, although spherically symmetric, leads to a three-dimensional problem in spherical coordinates. We may generalize the time-independent Schrödinger's wave equation to 3 dimensions by writing where 2 is the Laplacian operator and must be written in spherical coordinates for this case. The parameter m0 is the rest mass of the electron 6 in spherical coordinates. Schrödinger's wave equation may be written as the solution to equation 2.66 can be determined by the separation of variables technique. We will assume that the solution to the time-independent wave equation can be written in the form where r and are functions only of r and, respectively. Substituting this form of solution into equation 2.66, we will obtain. We may note that the second term in equation 2.68 is a function of only, whereas all the other terms are functions of either r or. We may then write that where m is a separation of variables constant 7, the solution to equation 2.69 is of the form. Since the wave function must be single-valued, we impose the condition that m is an integer, or m0, 1, 2, 3. 2.71. Incorporating the separation of variables constant, we can further separate the variables n r and generate two additional separation of variables constants l and n. The separation of variables constants n, l, and m are known as quantum numbers. The parameter n is referred to as the principal quantum number, l is the azimuthal or angular quantum number, and m is the magnetic quantum number. The quantum numbers are related by each set of quantum numbers corresponds to a quantum state that the electron may occupy. The electron energy may be written in the form where again n is the principal quantum number. The negative energy indicates that the electron is bound to the nucleus, and we again see that the energy of the bound electron is quantized. If the energy were to become positive, then the electron would no longer be a bound particle and the total energy would no longer be quantized. Since the parameter n in equation 2.73 is an integer, the total energy of the electron can take on only discrete values. The quantized energy is again a result of the particle being bound in a finite region of space. Objective: calculate the first three energy levels of an electron for the one electron atom. Solution: we have comment. As the energy levels increase, the energy becomes less negative, which means that the electron is becoming less tightly bound to the atom. The solution of the wave equation may be designated by NLM, where n, l, and m are again the various quantum numbers. For the lowest energy state, n1, l0, and m0, and the wave function is given by. This function is spherically symmetric, and the parameter a0 is given by and is equal to the Bohr radius. The radial probability density function, or the probability of finding the electron at a particular distance from the nucleus, is proportional to the product and also to the differential volume of the shell around the nucleus. The probability density function for the lowest energy state is plotted in figure 211a. The most probable distance from the nucleus is at RA0, which is the same as the Bohr theory. Considering this spherically symmetric probability function, we may now begin to conceive the concept of an electron cloud, or energy shell, surrounding the nucleus rather than a discrete particle orbiting around the nucleus. The radial probability density function for the next higher, spherically symmetric wave function, corresponding to N2, L0, and M0, is shown in figure 211b. This figure shows the idea of the next higher energy shell of the electron. The second energy shell is at a greater radius from the nucleus than the first energy shell. As indicated in the figure, though, there is still a small probability that the electron will exist at the smaller radius. For the case of N2 and L1, there are three possible states corresponding to the three allowed values of the quantum number m. These wave functions are no longer spherically symmetric. Although we have not gone into a great deal of mathematical detail for the one electron atom, three results are important for the further analysis of semiconductor materials. Figure 2.11 The radial probability density function for the one electron atom in the a. lowest energy state and b. next higher energy state. The first is the solution of Schrödinger's wave equation, which again yields electron probability functions, as it did for the simpler potential functions. In developing the physics of semiconductor materials in later chapters, we will also be considering electron probability functions. The second result is the quantization of allowed energy levels for the bound electron. The third is the concept of quantum numbers and quantum states, which evolved from the separation of variables technique. We will consider this concept again in the next section and in later chapters when we deal with the semiconductor material physics. The periodic table. The initial portion of the periodic table of elements may be determined by using the results of the one electron atom plus two additional concepts. The first concept needed is that of electron spin. The electron has an intrinsic angular momentum, or spin, which is quantized and may take on one of two possible values. The spin is designated by a quantum number s, which has a value of, or we now have four basic quantum numbers, n, l, m, and s. The second concept needed is the Pauli exclusion principle. The Pauli exclusion principle states that, in any given system, an atom, molecule, or crystal, no two electrons may occupy the same quantum state. In an atom, the exclusion principle means that no two electrons may have the same set of quantum numbers. We will see that the exclusion principle is also an important factor in determining the distribution of electrons among available energy states in a crystal. Table 2.1 shows the first few elements of the periodic table. For the first element, hydrogen, we have one electron in the lowest energy state corresponding to N1. From equation 2.72, both quantum numbers L and M must be 0. However, the electron can take on either spin factor 1/2 positive or 1/2 negative. For helium, two electrons may exist in the lowest energy state. For this case, Lm0, so now both electron spin states are occupied and the lowest energy shell is full. The chemical activity of an element is determined primarily by the valence, or outermost, electrons. Since the valence energy shell of helium is full, helium does not react with other elements and is an inert element. Table 2.1 Initial portion of the periodic table. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. The third element, lithium, has 3 electrons. The third electron must go into the second energy shell corresponding to N2. When N2, the quantum number L may be 0 or 1, and when L1, the quantum number M may be 1, 0, or 1. In each case, the electron spin factor may be 1/2 positive or 1/2 negative. For N2, then, there are 8 possible quantum states. Neon has 10 electrons. 2 electrons are in the N1 energy shell and 8 electrons are in the N2 energy shell. The second energy shell is now full, which means that neon is also an inert element. From the solution of Schrödinger's wave equation for the one electron atom, plus the concepts of electron spin and the Pauli exclusion principle, we can begin to build up the periodic table of elements. As the atomic numbers of the elements increase, electrons will begin to interact with each other, so that the buildup of the periodic table will deviate somewhat from the simple method. Summary. A few basic concepts of quantum mechanics, which can be used to describe the behavior of electrons under various potential functions, were considered. The understanding of electron behavior is crucial in understanding semiconductor physics. The wave-particle duality principle is an important element in quantum mechanics. Particles can have wave-like behavior and waves can have particle-like behavior. Schrödinger's wave equation forms the basis for describing and predicting the behavior of electrons. Max Born postulated that x2 is a probability density function. A result of applying Schrödinger's wave equation to a bound particle is that the energy of the bound particle is quantized. A result of applying Schrödinger's wave equation to an electron incident on a potential barrier is that there is a finite probability of tunneling. The concept of quantum numbers was developed from the results of applying Schrödinger's wave equation to the one electron atom. The basic structure of the periodic table is predicted by applying Schrödinger's wave equation to the one electron atom and using the Pauli exclusion principle. Glossary of important terms. De Broglie wavelength, the wavelength of a particle given as the ratio of Planck's constant to momentum. Heisenberg uncertainty principle, the principle that states that we cannot describe with absolute accuracy the relationship between sets of conjugate variables that describe the behavior of particles, such as momentum and position. Pauli exclusion principle, the principle that states that no two electrons can occupy the same quantum state. Photon, the particle-like packet of electromagnetic energy. Quanta, the particle-like packet of thermal radiation. Quantized energies, the allowed discrete energy levels that bound particles may occupy. Quantum numbers, a set of numbers that describes the quantum state of a particle, such as an electron in an atom. Quantum state, a particular state of an electron that may be described, for example, by a set of quantum numbers. Tunneling, the quantum mechanical phenomenon by which a particle may penetrate through a thin potential barrier. Wave-particle duality, the characteristic by which electromagnetic waves sometimes exhibit particle-like behavior and particles sometimes exhibit wave-like behavior. Checkpoint. After studying this chapter, the reader should have the ability to discuss the principle of energy quanta, the wave-particle duality principle, and the uncertainty principle. Apply Schrödinger's wave equation and boundary conditions to problems with various potential functions. Determine quantized energy levels of bound particles. Determine the approximate tunneling probability of a particle incident on a potential barrier. State Pauli exclusion principle. Discuss the results of the one-electron atom analysis, including quantum numbers and their interrelationship as well as the initial formation of the periodic table.